Hey everybody, it's Pete here, and I have a little confession to make. I am addicted to puzzle games. I've played through Portal 1 and 2 multiple times. I played through the Talos Principle multiple times, which, by the way, is an amazing, amazing game. I could not recommend the Talos Principle enough. It is really awesome. But recently I discovered another game by accident. I was researching some equipment to buy for quantum experiments, and I'm setting up a little quantum physics lab, and I realized how expensive it was, and I went, okay, maybe before I buy all this equipment, I should do some modeling in software and see if I can save myself some money, and then I can proceed to do the experiments in the real later. And so I was looking for quantum physics simulations, and what did I stumble upon? This quantum game. So I burned through this quantum game, all 35 levels in the space of just a few hours one afternoon, and I enjoyed it so much, these brain teasers. I love to just pour myself, a couple of pots of coffee, put on some JS motherfucking Bach, and just geek out, nerd out. And so that's what I did. And so I'm going to show you how to beat the quantum game if you're so inclined. Maybe you've tried it and you got frustrated, you got stuck. There's not a lot in the way of hints and stuff when you play this game. You kind of have to just use your brain. And I could see how somebody might get stuck. There were a few times where I was definitely scratching my head, had to try a few different things until something worked. So I'm just going to give you a walkthrough from start to finish on the solutions that I came up with for the quantum game. And now this is a sort of a simplified quantum physics lab where the goal is, you have a laser that fires one photon, and you bounce it through some mirrors, and you've got the partially silvered mirrors, and you've got you've got all kinds. You have like a rock that it can hit, and you've got detectors, of course, and you've got things that absorb it, and you've got things that change the phase of it, and things that change the polarization of it. I mean, there's all these things. And as you play the game, they throw more and more of these tools at you, and you learn how to use each of these little tools in order to achieve the objective, which is generally to get the photon from that laser to strike certain detectors. And there are also these things called bombs that if the photon strikes the bomb, it will blow up, and of course you lose. So usually the goal is pretty much get the photon into detectors, sometimes multiple detectors. Don't hit the bombs. And you do this by placing components on a grid in certain spots strategically. So I'm going to show you what the game looks like, and I'm going to show you how I solved the levels. Okay, here's how I'm going to do this. In this one browser here, Firefox, I have not played this game in this browser, so you can see that it does not show these levels as being completed, and it's just the default, how it loads from the start. In this other browser here, Chrome, you see that I have played through these levels, so it has my solution pre-recorded here. So take, for instance, this first level here. You press the play button, and the laser here will fire a photon. And you see that it strikes the rock. Well, that's not what you want, right? So, but you also see there's a mirror here. Now, when you see these squares here that are grayed out, that means you can't move them. Okay, so that means you have to place objects somewhere else. Over here are the objects that you can place. So I can click and drag this, which is a mirror, and I can place it here. Obviously, in that orientation, it's not going to do anything. So, what we want is to orient it in a way that it will bounce the light down into this mirror. So, when you bounce the light downward, and it's going to hit this and bounce this way. And okay, we're almost there. We need one more mirror, right? So we place one more mirror, and oh look, that's the last mirror that we have. Now we can circumnavigate the rock. And it goes into the detector. And that is the goal, to get the photon into the detector. So this next one here, what I usually like to do is I'll press play and just see what happens if I do nothing, right? So, okay, so if I just press play, it fires the laser, it hits one detector. But you'll see that there are actually 5 detectors. And it says, goal, make the photon fall into 5 detectors, some probability to each, total of 100%. Well, how am I going to do that? Well, you have to split the beam, because there's only one beam, right? So that's what you use these beam splitters for. what did I do? Okay, it hits this one and bounces up, goes through, bounces this way, goes through, bounces up. Okay, and then over here I've got one that is doing like so. Okay, so let's see if that works. Great. So now, right here, you see the probabilities. You see these probabilities? This is the probability that the photon will strike any one particular detector. So you notice this one was only 13%, whereas the other ones were like 25%. It's because every time it goes through one of these, there's a 50-50 chance it's going to go this way versus this way. So if you chain enough of these together, you'll see that you'll get weighted probabilities where it's more likely one way than the other. So again, you've got 3 detectors, 1 source. You're going to have to do some splitting, so this should send it up and through, but that's not enough. We also need it to go down. So let's see, how did I solve this one? I solved that one like so. So you can just place the other mirror like that, and there you go. So you see the probabilities of each impact. So I'm not going to play through every single one of these. I'm not going to talk about every single one of them. They get pretty complicated. So this is an interferometer here. I think this would be a Mach-Zehnder interferometer, I believe this would be called. So you'll notice the light comes in like so, and then it gets split, and then the two arms post-split get recombined. Now, if there's one photon, you might be thinking to yourself, how does one photon get split into 2 things when one photon is the smallest? You can't split a photon, right? From what I understand, the physics of it is the photon actually splits into its own antiparticle. So, and it doesn't take both paths exactly, but it can combine and interfere. So with the Mach-Zehnder, you're going to see when it recombines, it's going to come out as just one beam instead of going into 2 beams as it would if you just had the one splitter. When you recombine, it's going to come out in 1 beam. Now that's due to constructive and destructive interference. You've got constructive interference going one way, destructive going the other way, and it's just a very weird thing. But it's been experimentally verified that this actually does happen. It's not just imaginary. So what did I do for this number 4? I did something like this. So splitting it, recombining, coming out of the Mach-Zehnder, splitting again. It's like I made another Mach-Zehnder. There we go. And so the goal changes for each level. You may want to, it may be 100% probability that it needs in order to get to the next, it may be 100% probability that you need, or it may be a lower probability. But usually when there's a bomb, they want you to have 0 probability of blowing up the bomb. I don't recall any time where it was okay to have any probability of blowing up the bomb. So like for instance here, okay, it said there was a 25% chance it's going to blow up the bomb by default. 25% chance it'll hit the detector. Now this glass here, okay, that's not absorptive. I guess the other 50% is that it would just go off into space down here. So, we're going to need to do something about this. They say, you don't want to blow up the bomb, but you do want to hit the detector. How did I solve this? Well, I put another glass slab here. These glass slabs, it says over here, higher refractive index makes light slower. We set its thickness so it retards the phase by lambda over 4. Useful for changing interference. Okay, so now when we fire this thing, this is going slower through this arm. So now it has changed. Normally it would the photon would come out in the other direction and blow up the bomb potentially. Now we're making it so it only comes out in this direction, and that's due to slowing it down a little bit as it goes through this arm. So let's see, what other levels do we have here? Level 6.
guiding interference. So this one's interesting. You have a bunch of Mach-Zehnder interferometers, and by default, you've got these two interferometers feeding into each other, and it's coming out over here with 100% probability. But oh wait, there's another detector over here, and it says down here, one detector feels sad and forgotten. Be fair, give every detector a chance. And then you see the detectors here. One of them is green, the other one is not. So your goal is to get all the detectors green, usually, you know. So how did I solve this particular one? Well, looks like I placed some of these glass slabs in here, and you start out on this level, you've got 3 of them. So I placed them here, here, and here. Now let's see what happens. These are going to slow down the light as it goes through these Mach-Zehders. See, now it's splitting it instead of coming out in one. Alright, and so even though the photon was detected here on the left and not here on the right, there's 50% probability that it would have come up over here. And that's enough to say, okay, the detector will detect it a certain amount of the time. But, you know, if it's the case that the detector would never detect it, then usually that's not the solution. So what do we got here? Got another Mach-Zehnder interferometer. And it's coming strictly down into this detector. So again, one detector feels sad and forgotten. Okay, so we need to come up with a way of getting this to split. How do we do that? Oh, there's a rock. Okay, well, I don't know how much you know about interferometry and quantum stuff, but if you were to place a rock somewhere on one of these arms, it would cease to be an interferometer. It would not function as an interferometer, because interferometer, you're splitting the beam into 2 beams and then it's interfering with itself. Well, if you no longer have 2 beams, then you no longer have any interference, which means when it hits this partially silvered mirror, this beam splitter, it's just going to split it into 2 beams. So let's see if that's correct. Yeah. Now here's the weird thing. You notice that it said, when it hit the rock, it said not here. That means the photon didn't go this way. The photon went this way. So how does it even know that there was a rock there? Well, this is like putting your finger in the path of a laser in a Mach-Zehnder interferometer. You will observe the same thing. The interference will disappear. It's pretty bizarre. I'm not sure that anybody fully understands how it works. But okay, so that was 7. Yeah, so that was my solution. So 8. Michelson-Morley. Okay, I don't know if you remember the Michelson-Morley experiment, but it's a famous physics experiment that proved that there's no electromagnetic ether. And, well, I'm not going to go all into it, but you should read up on the Michelson-Morley experiment. This is called a Michelson interferometer, and it's going to look like a big cross. So, how did I implement the Michelson interferometer? Like this. So, these mirrors should, you could probably put them any distance from here. I just put them close by. Because why not? It's easy to align that way in real life. But see what it does? It splits off into 2 arms. And yeah, let's try it. Let's put a gap of I don't know, 3. 3 empty spaces between the beam splitter and each mirror. And I think you'll see it does the same thing no matter how long the arms are. But the idea is that these arms, if they're a fixed relation distance relative to each other, then this interference pattern should be the same. And if you were to rotate this thing, there are certain implications for the very fabric of space-time that has. Well, I don't want to go into it; it's too complicated. But read up on it is extremely interesting. So here we have a phase problem, and again, the goal is to get this into the detector here. So, I mean, the obvious thing to do is to put some mirrors, like so, or hell, let's put them like right here and see what that does. And in many cases, you may have to experiment here, okay? So, like, 50% probability, pretty good, right? Well, they want 100% probability of hitting this detector. So, this is one of those ones where you probably just have to experiment. If we go over to my solution here, what was my solution? It was a specific placement of the mirrors. And that specific placement of the mirrors down here and over here leads to just the right phase, so that when the light comes back to this beam splitter, it's in just the right phase to make constructive interference here, destructive interference here. Because if it's constructive here, it's going to go back into the laser, right where it came from, right? So you want it destructive here, so nothing comes out this direction, and you want it constructive here, so all of it comes out that direction. And you know, really, there's probably a way to do it without trial and error, but with problems like that, I end up just doing trial and error, and it seems to work okay. Number 10, what do we have here? Beam splitter. Oh, that's not good. Look at that. Boom! Okay, 50% chance of blowing up the bomb. 50% chance you're going to strike this detector here. Looks like there's another detector over here. Okay, so usually you want to hit all the detectors, and it says nothing else matters when you have a 50% chance of setting off a mine. So you'll see this nothing else matters thing. No matter what probability, if it's a 1% chance you'll blow up the bomb, that will disqualify you from beating the level. And there were times that I got a 99% probability that it's safe. 1% chance of blowing up the bomb. Not good enough. It has to be absolutely 0 for you to win. So what did I do? This is number 10. Let's go over here. Okay, this is what I set up here. Looks like there's probably some interferometry going on here. And, okay, then we get split off. And 75% this detector, 25% that detector, and nothing left for the bomb. And this is all using interference. These are legitimate topics in physics. These are real phenomena. It strains belief that this stuff can happen. This is funny. So you've got a laser that's pointing right at the bomb. I wonder what would happen if I were to pull the trigger on this laser. There goes the laser, and kaboom. Okay. So what do? Well, we only have one tool. It's not a mirror. It's an absorber. Filter with 50% absorption probability. Okay, so if you were to put this here, right, there's a 50% chance it would absorb it, 50% chance you'd blow up the bomb. And what do you know? It absorbed it. Great. Okay, so but there's a 50% chance it'll blow up the bomb. What about this? Well, if it gets through here, there's a 50% chance this will absorb it, right? So 50% chance of blowing up the bomb becomes a 25% chance of blowing up the bomb, and 12.5% chance, and 6.25% chance, and so on. So you gotta put enough of these together, that it's confident that it's basically 0. Notice that it's going to be like an asymptotic curve. It's never going to quite reach 0, but it's going to be arbitrarily close to 0 with this many things. It's going to be 1 over 2 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 over 2 to the 9, which, what is that, like? I don't know. So yeah, it's not very probable that you're going to strike the bomb through all of these, absorptive materials. What are we on? 12 here? Oops, wrong one. Okay, 12. Match intensities. Okay. So this is, I think, going to show that. Yeah. Okay. So we got a bomb here. 2% chance by default. 73.25. So it's probably going to hit one of these detectors, but it might hit the bomb. So we want to make it so it won't hit the bomb. And intensities are important with interferometers. If you have two beams that are slightly different intensities that are being combined, you're not going to get 100% probability in one arm of the output and 0 in the other. The intensities have to match. So let's go over to my solution here. And what did I do? Well, I put an absorptive neutral density filler right here in this interferometer here. So let's see what happens. All right, you see how it came out? 100% from these, and nothing down here. That's the goal. In many cases, you may need to do some trial and error to determine these things. Rotating polarization with sugar. So sugar water does something weird. It actually changes the polarization of light, which is something I didn't realize, because it's like, so what is it, a chiral molecule or something? It says down here, table sugar is a chiral molecule. It does not look the same as its mirror reflection. We put it in an amount so it rotates the polarization by 45 degrees. So, well, obviously, we're going to get the photons down here, so we got some mirrors, and we can place them in a way that they'll get the light down there. In this case, I don't really see that these sugar water things are really doing anything in this particular level. I think they're just trying to show you that the light goes through them, but it changes how it wobbles. Later on, you'll see that that there are applications to the sugar water. Okay, so here, these polarizers, anisotropic polymer strands, capture electric oscillations parallel to them, used in photography. That doesn't really tell you much, but you'll see how this is diagonally oriented, another diagonal, different diagonal, horizontally oriented, these stripes. And you've got a couple mirrors here that are obviously going to bounce, like retro-reflect the light right back toward where it came from. Okay, so you want to get the light to go through these, but you can just tell if you know anything about polarization, that is the opposite polarization of that. It's like 90 degrees off. So anything that's going to go through this is not going to go through this. And we'll see that, I'm sure. So it went through this, but it hit that. Okay. So it's definitely going to be absorbed by one of these, right? So the goal then is to change the polarization of the light using the sugar water, so it'll pass through all of these. And rather than trial and error this thing, this is the solution I came up with. So we're changing a little bit, goes through that one, changes it more, goes through that one, changes it a little more, goes through that one. And this is like one of those trial and error sort of ones. You're going to end up monkeying with it unless you're just really sharp. And look at that. It went through all of them. Great. So then, apples to apples. We've got more polarizers. And, yeah, and it looks like, well, let's just see what my solution was to that one. If I sat here thinking about it all day, we'd never get through this, so I'm just going to show you my solutions. Okay. Yeah, and we've got basically even probability here, 50-50, great. And two green on detectors, 100% down here. And it's not always 100% probability that they're after. Sometimes it's a lower percentage. Sometimes it's just not possible to get 100% probability, and that's fine. Okay. Yeah, so here's a weird one. So in this case, this one's horizontal polarization. This one's vertical polarization. How is any photon with horizontal polarization going to get through vertical polarization? Well, I seem to recall how this one worked. If you have nearly the right polarization, say you're 45 degrees off, you can kind of like swage the light, to get it through. So let's see what I did. Yeah, it looks like I put my polarizer kind of between the two. So this one's horizontal, this one's vertical. I put it diagonal. So it goes through this one, and then it kind of twists it or something. And in this case, it struck this one, but in some cases, it will go through. In a quarter of the cases, I can get it to go through. So very interesting. And I love this because, you learn so much about quantum physics. If all this is legitimate, and I believe it is, you will learn so much about quantum physics. You'll have a real hands-on experience doing quantum physics experiments without spending thousands of dollars on the equipment, which I think is just awesome. So sugar recycling. Sometimes there's hints as to what to do. So in this case, the hint actually helped me, right? All I have is 5 sugar waters here. Where do I place them? I got to place some in here so it goes through here, and then it bounces here, 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 goes through here, and then comes back down. Well, what does the term recycling mean? It means you're reusing something, right? So the beam comes through this direction, and it eventually comes down this direction. Recycling would be placing one here where it's going through it multiple times. And if you look at my solution, look, there's the recycled sugar right there. It goes through there, change the polarization, goes through there, change it some more, goes through there, and boom, we've recycled our sugar water, and boom, we're in the detector, 100% probability. Awesome. Polarizing beam splitter. These are beam splitters that change the polarization of the light. And, you'll want to read the descriptions on these things if you simply... There we go. if you simply hover the mouse over it. So it's all going into this, and the goal then is to get it to split amongst all 4 of these detectors. If you put the mouse over one of these, you can see polarizing beam splitter, reflects vertical polarization, transmits horizontal polarization. So it's sort of like several components in one. Let's go over to 18 and see what my solution was. Well, I dropped a bunch of sugar waters in there and some beam splitters, and here we go. There we go. We got 4 out of 4 detectors. In this case, they're all 25% probability. Awesome. 19. Okay. More polarizing beam splitters. And you can tell the difference between these and regular beam splitters because these are cubes. In real life, I think there's cube versions of non-polarizing beam splitters, and you can't just tell, oh, that's a cube, that must be polarizing. No, in real life, the non-polarizing ones are often cubes as well. But in this game, they have to represent it somehow. So it looks like we got a bunch of sugar waters in here, and my solution, and we're using the sugar waters to control how the light passes through these polarizing beam splitters. In some cases, we want it to bounce like this. In other cases, we might want it to split. So we sort of guided it down and through this loop, and we had to polarize it just right so it would go through this absorptive polarizer, and bang, hit our detector. Number 20. Perpendicular are different. I love the way these guys talk sometimes. Okay, so it's bouncing up. It's going across. Doing a little loop-de-loop. Oh, this isn't good. You see? So it didn't hit the bomb, but it had a 50% chance of hitting the bomb. So I knew when it was coming down to this beam splitter, there's a very good chance it's going to bounce off and hit that bomb, and we can't have that. So let's go over to number 20 and see what I did for that one. Okay. Looks like sugar water is all you get in this one. And I use the sugar water to change how the light travels. And oh, there we go. So now it's coming back, and boom. It interferes with itself right here at this beam splitter. That forces it to go in one direction only. So we have constructive interference on this leg, this output of the interferometer, and destructive here, which means you'll never see a photon here, and you'll always see a photon there. Pretty cool, huh? So by adding more light, you actually subtracted light from here. It's unreal how this stuff works. Einstein was very dubious of this, by the way. Einstein, he criticized... Oh, I wonder what's going to happen. Oh. Einstein criticized quantum physics as, he said it was spooky action at a distance. And he said that God does not play dice with the universe. Meaning that things are not just random. Things happen for a reason, and we should be able to predict what's going to happen. It shouldn't just be, completely random and weird. But, it turns out that Einstein, as smart as he was actually wrong in this and many other cases, because it turns out that you can have spooky action at a distance. It's called, I'm thinking I'm just going to go to my solutions while I'm rambling here. You can have spooky action at a distance. It's called quantum teleportation, and things are completely random. In some cases, it's called Heisenberg uncertainty. So there are many cases where you just don't know what's going to happen, and no matter how many PhDs you have and how much calculations you do, you cannot compute what is going to happen. All you can compute is a probability. So Sagnac, Michelson-Morley, this is 2 interferometers combined. So the Michelson-Morley is this one here. You notice the big cross shape. It's splitting it here. It has this arm here and this arm up here. But instead of just a mirror up here, it's got this whole other thing up here. And this thing up here is a Sagnac interferometer. So notice when the light comes up here, it hits this beam splitter, and it actually travels in 2 directions at once. So it circulates this way, and it circulates this way. So that's called a Sagnac interferometer. And we've got it configured here using this vacuum jar, which speeds up the light to have constructive interference here, destructive here, so the light has to come back down this direction. And then the placement of this mirror here is critical. And that was something, I'll be honest, I determined that purely experimentally. I moved it around until it worked. And If you got a better method, please do share it with me, because I just don't know that there is a better method. 24, Sweet Madness. Well, you can tell why they call it that, because you end up using all this sugar water here to change the polarity multiple times. Okay, I'm going over here, I'm going down. It's going to make a big loop here. Yeah, there we go. Avoiding the bombs. Okay, and into the detector. Right on. So, and the sugar water changes the polarity. The polarity indicates what the light does when it hits these polarizing beam splitters, whether it's reflected or transmitted. And you just gotta, play around with it until you get it to do what you want. Sounds like we got multiple interferometers in one here. Interfrenzy. And see how when they combined here, they only went this way. Constructive interference this direction, destructive in this direction. Same thing here. Destructive this way, constructive this way. We don't want the light going into the bombs, so we're channeling it toward where we want it to go. Faraday and mirrors. Oh, okay, so the Faraday polarizer is very interesting. It's like an electromagnet through which the light travels. And the light will be polarized in one way as it goes through one way, and then if you bounce it back through the Faraday polarizer, it'll change polarization yet again. Rotates polarization with magnetic field by 45%. Has different symmetries than sugar solution. A building block for optical diodes. Yeah, so these things, they're similar to the sugar solution, but they are not the same. Because the sugar solution does the same thing no matter which way the light's going. These things will change the polarization depending on which way the light's going. You can actually make one-way mirrors using Faraday polarizers. So it's called an optical diode. So as you go through here, notice we're trying to keep the light from coming back this way, right? Because if the light bounces back this way, what's it going to do? Well, it might go through and hit this, but there's a 50% chance it's going to bounce up here and boom. We can't have it coming back. So by placing this absorptive polarizer here and this Faraday rotator here, we're making it so that if the light bounces back, it's actually being twisted, and then it's going to hit this polarizer and it's going to just stop. Because when this thing, the Faraday rotator, twists the light, it'll now be a different polarization than this horizontal. It'll be vertical or something. So when it hits this, bang, it's just going to stop right here, and it will not come back and blow up the bomb. So that's called an optical diode. Sagnac twist. Okay, we don't want to bounce up here, so we make it so it transmits through only. And this is just madness here. Okay. Right into the detector. Yeah, we don't want it coming back here because then it could bounce down to there. So 100% into the detector, 0% in the bombs. Sweet, sweet. 9 polarizing beam splitters. Yeah. Alright. One-way mirror. Okay, this is what I'm talking about with the Faraday rotators, how you can make one-way mirrors with them. Look at that. Wasn't that beautiful? Sweet Faraday. I will say, I mean, some of my solutions to these did take a little while. I didn't always see the solution clearly in my mind. I would just sort of work through it, be like, well, I got to get the light to go here. I don't want to go toward the bomb. I do want to go toward the detector, and just sort of monkey with it. And in some cases, yeah, there was a lot of trial and error involved in coming up with these solutions, which is why I felt like sharing them, because if somebody else was frustrated, I could see them just giving up. Because this game, I could see how this game could just break your brain. There we go. Again, constructive interference here, destructive here. 100% on the detector, 0% on the bomb. That's what you want. Interfering polarization. Oh, look at that. So nice. And if I recall, this is the last official level, a bit of a lot. I'm just going to go back over to the original here. Okay, so when you hit this, okay, it might be absorbed by that 50%, or it might go hit this, and 20%, 25% hit a rock, 25% hit a bomb. Either way, that's not doing you any good, right? So you got all these tools over here, but they don't really give you enough for an easy solution. You know, if they just gave you a bunch of mirrors, that'd be super easy. You can just bounce them into the detectors, but they don't. And this is one of those ones where you have to use all these tools. So I'll just show you what I came up with this here. And this one did take me a little while to figure all this stuff out. And you notice that this is changing the speed of light a little bit, and this is absorbing some light in order to probably to match the intensity. So all this stuff is absolutely critical to make this thing work. I used every single component. Yeah, and notice even though it's being absorbed here, there's a 25% chance it'll hit this detector, 50% chance it'll hit that detector, and no percent chance on the bombs. And that's what you want. In this case, this is one of those cases where you only need 75% probability of hitting one of these detectors, and I don't think it's possible to get to 100. But the real critical thing is you want 0 on the bombs. The bombs have to be 0. If the bombs are anything but 0, it won't work. And I seem to recall I came up with a lot of solutions to this one where, I had a very, very tiny, 1% probability of hitting the bombs, 99% probability of hitting the detectors. Not good enough in order to pass the level. Now this is an extra level. They call it level 1, which is weird because there's already a level 1. The actual level 1 is that. I'm just going to call it level 35. So you're on level 35, flowing with the current. And they call it, well, I guess I have to go to 34 and then, I can't jump there from here. Well, okay, so here's the solution that I came up with. And there may be multiple solutions. Notice, you do not want to come off of those arms there. And look at that. It's all due to the polarization. Which way the polarizing beam splitters send it is all to do with the polarization of the light when it hits it. So that was my solution to this one. So those are all the levels. This is like a bonus level, flowing with the current, 35. But here's the cool thing. This sandbox level, this infinity symbol here, you can play around with making your own quantum physics experimental setups. So in this case, I think this is like a version of the Michelson-Morley Sanyak from the other level. I made it larger and stuff. But you can play around and do your own quantum physics experiments without spending thousands of dollars on equipment, which I think is great. So as one last thing, let's see if can I find out about these guys. No, that's about the game. I want to find out about the guys themselves who made this game. It says Eternal Beta version by Piotr Migdal, Patrick Hess, and Mikhail Krupinski. Oh man, there we go. Mikhail Krupinski. So these guys, I don't know anything about them, but other than it's clear that these guys are really, really ridiculously smart. Not only for understanding quantum physics enough to make this game, but understanding how to program and make a very clean, easy to use game that just twists and bends your mind in all sorts of ways. I highly suggest that you check out the Quantum Game. So the Quantum Game can be found at play.quantumgame.io. Play.quantumgame.io. And I highly recommend it. It's a really fun game. If you're into puzzle games, check it out. And I'll probably show you some actual quantum physics experiments in the near future since I am building a quantum physics lab. But I figured this would be a quick fix for me to learn a bunch without spending money. Cheers.